So let's move on with it. So the incretin effect here. And you all know this figure, I know that, so we don't have to spend much time about it. But I'd much prefer to show the incretin effect in a different way with these old experiments by Michael Nauck. And what he did was to give people glucose, and he gave them either 25 grams of glucose or 50 grams of glucose or 100 grams of glucose orally. And this was in the days when, we were doing all these incretin experiments. So he also did an isoglycemic glucose infusion. So these were the concentrations after the oral administration. And you can see that he did very well in reproducing these excursions with the intravenous infusion. So now what happened? So up here you can see that the 25 gram gave this kind of excursions. And for that he needed 20 grams of glucose. 25, 20. Well, here's the 50 gram, and again, it took 20 grams of glucose. And over here, it's 100 grams of glucose, and again, it took 20 grams of glucose. And this is really, really remarkable. So regardless of how much glucose you take in, you get the same kind of glucose excursions, as you can clearly see down here. That's how powerful this effect really is. Here it's 80% of the glucose that you take in orally that is disposed of by some mechanism. It is removed from the circulation. And I'm pretty sure that this is extremely important for long-term, cardiovascular everything. And why is that? What happens? Well, you can see that here. Insulin secretion is augmented from some response to a larger and to a very large response over here with a large dose of glucose. So this is what happens. This is the incretin effect, and this is the power of the incretin effect. So consider it as a very dynamic process. The more glucose you take in and other nutrients also, the stronger will this thing be. So what is the mechanism behind the insulin secretion? And that is also known. So these are studies out from Philip's laboratory. Jonathan Bakker did them, and here we gave 25 grams and 75 grams and 120, so more or less the same. And up here you have the GIP, that's one of the hormones responses, and the small dose and the larger dose and the big dose here. And here down here we have GLP-1, again showing these very clear dose-related relationships. So this explains the difference in insulin secretion very, very clearly, as beautifully shown in these experiments here. So that's how I like to present the incretin effect. It's really powerful. So how much do they do each of these hormones? And this was what Tina Wilsbøl did at a very early stage in her career. But it's a beautiful experiment. So what she did was to clamp glucose in volunteers here at their fasting level, and then took it up by 1 millimolar and 2 millimolar, covering what we have in meals, the normal concentrations. And then she put postprandial concentrations of either GIP on top of those clamps or GLP-1. And these are the concentrations you see after a meal. So this is physiology. So what happened to insulin secretion? And this is what happened. So you see that even at the fasting glucose levels, these physiological increases in GIP and GLP-1 resulted in a nice insulin response. So they do this from the very beginning of a meal. They're active from the start. And as glucose increases, they become more powerful. And as it comes up to 2 here, they're very powerful in terms of stimulating insulin secretion. So this is what really happens. Over here, we're looking at glucagon secretion. And again, the glucose in itself will inhibit glucagon secretion. And it does that very nicely, as you can see. With GIP, nothing really important happened. But with GLP-1, there was a suppression of glucagon at every one of these steps. So they are different in this term, these two hormones. Now, together, they act on insulin secretion, of course, and these are old studies by Katrine Ørskov working with Michael Nauck, where they infused GIP and GLP-1 to people. And you can see that this was done while clamping the glucoses, but you can see here the insulin concentrations here. They increase in an additive manner. As you can see over here from the columns, it's a completely perfect additive effect of GIP and insulin in these healthy controls. So that's how they do this. Now, a more elegant and also more powerful tool in physiology of this kind is to use antagonists against the receptors. So do we have antagonists? The problem with antagonists is that you have to have somebody develop the antagonists for you. Otherwise, you can't do it because they're not there hanging from the trees. You have to do something. So GIP was discovered here in 71, and GLP-1 here in 86. But then already in 90, Raufman and Eng discovered the Exendin 9 to 39 and showed that it was an antagonist of the Exendins. And then very soon it was also discovered, also with these people in collaboration with various others, that 9 to 39 was also an antagonist for the human GLP-1 receptor. So that was kind of established then. And then in 1998, people started doing studies with Exendin 9 to 39. I knew this, and I was also very interested in infusing Exendin 9 to patients to see what happened. And I was writing this letter. I was sitting there day after day trying to put the words in the letter to the health authorities of Denmark and saying, we are going to use this peptide from the venom of the lizard, of the Gila monster to block actions of GLP-1. And I simply couldn't do it. And this is extremely exciting, considering that in 2006 there was a big thing about GLP-1 and pancreatitis, and officers of the FDA wrote in New England Journal of Medicine that it was logical that this venom from the Gila monster could create pancreatitis. They said that. I have it, a slide of it. It's beautiful. Well, nothing happened, of course, and so it was all right. But I still admire Scherer and Bloom, who did these studies, that they dared do it at all. And Bloom even told me that his daughter was the first volunteer to receive it. So quite something. Okay, then, as you can see, there's a big break here. And then, finally, we found another GIP antagonist that even could be used for human studies. And then, the studies developed, and it's actually interesting that 9 to 39 is now going to be a drug for post-bariatric hypoglycemia. It's most likely going to reach the market here. So it has been granted a breakthrough therapy designation, an orphan drug also. So let's see what happens. But many studies have. So we have these two antagonists, and now we can use them. And here's the GIP receptor antagonist, and it is a high affinity. It's a truncated form and an amidated form of GIP. It has a high affinity for the GIP receptor, as you can see. It has no agonistic properties, which is very important. Some of the early ones, they did have that. And, you can see that it's completely competitive antagonist by this linear shield plot, which is a beautiful result. So we can start using it. So if you use, these are studies by Gaspia, and you can see that here she is looking at insulin secretion with GIP and with the antagonist and the placebo, or with the combination. And if we now have a look at it, then you can see that this is with GIP, this is with, if you block with the antagonist, and then if you look at the amplification here, you get that you have inhibited the response by some 80%. I guess that is as good as it can be. It's always difficult to at the edges of these results to see what really happens. Okay, so what happens? Now, this is the most important slide of them all, because what it shows is that if you combine the GIP receptor antagonist and the GLP-1 receptor antagonist, you get glucose intolerance. That's what happens. So you have here the placebo group, and then you give them those blockers, and you can see that now you have an individual with glucose intolerance. So that's what the incretin does. Wow. And so I've been waiting, for 20, 30 years to see this, that in fact it's true. It's not something we've cooked up in our crazy brains. It is true. If you take away the incretin action, then you develop glucose intolerance. That's the major result of this. Okay, so if you look at insulin secretion, and that's a little bit difficult, of course, because you change the glucose now. So you have to adjust the insulin responses for the changes in glucose. And the way we did this was to look at C-peptide glucose AUCs and divide them with, normalize the C-peptide for glucoses. And if we do that, then you can see that these treatments, they greatly reduce the insulin secretion, as you would expect. And now you can start calculating things. And this is what so we published this in Diabetes in 2019. And Michael Nauk was doing an editorial, and where he sat there at his desk and did some calculations. He loves to do that, always does it, and came up from, they're extremely complicated, those calculations, and came to the result that GIP was responsible for 44% of the insulin. Glucose itself was responsible for 33%, which is consistent with what we thought, and GLP-1 for only 22%. So he didn't have, at that time, access to the real data. We did that afterwards, and here are the results. So GIP 45%, glucose 26%, and GLP-1 29%. That's what it looks like. So now you know which one is the most important in terms of insulin secretion. That's GIP. And GLP-1, what the hell about GLP-1? That's different somehow. Now, I have to say that Exendin 9 is a very difficult tool. And the reason for that is twofold. First of all, 9 to 39 may have some inverse agonist action. That means that it will inhibit the receptor even if there is no ligand present. And it does that to some extent. So, you know, normally you would say that with Exendin 9, you block the GLP-1 receptor on the beta cell and that's it. But that's not it. There's also a very important GLP-1 receptor on the somatostatin cell. If you block that one, perhaps by inverse agonism, you also block the release of somatostatin, it goes down. Somatostatin at all times controls glucagon secretion. So now you have an increase in glucagon, and that glucagon no doubt will influence insulin secretion and cause a rise in glucagon in the first place, and also impact on hepatic glucose production. So what you get when you give Exendin 9 is an increase in blood glucose and an increase in glucagon. And you always do that. And that, of course, complicates matters. So you can't really completely rely on Exendin. It's complicated. But it's just a reservation. Let's keep it the way I showed it, because that's nice. Okay, so so we have these two hormones, and now if you put them together in a single molecule, then you have tirzepatide, and I'm sure that Sten will present some of the real data. These are just the phase 2 results, where with these doses you had tremendous effects on hemoglobin A1C and on body weight. You know, you've seen them all, you all know them. You all know that during those 2 hours in 2018, when these data were presented in Berlin at the AASD, the stock value of Novo Nordisk fell by $48 billion. That's how kroner it was. Sorry, kroner. That's how much it was. You know, this is really dramatic. They're back. Don't worry. So just the result of SURPASS-2, that's one of these phase 3 studies with tirzepatide, where you have now that 50% of the patients you put on therapy have A1C levels below 5.7. That is ridiculous. And at the same time, you have weight losses of 10% or 10 kilograms here with that dose. So incredible results. So we could stop here and indulge in the fact that a monomolecular combination of the two powerful incretin hormones, GIP and GLP-1, is the most powerful anti-diabetic agent discovered so far. But in fact, this is completely incomprehensible. And why is that? Well, here's a study, again, with Michael Nauk that we did. Infusions of GIP, GLP-1, and co-infusions of the two in people with type 2 diabetes. And these were the results, the concentrations, high concentrations of GIP, also of GLP-1, also of the intact hormones that we also measure. So they're getting good doses of both. So what happened? So whenever you give GLP-1, you get a lowering of glucose, which is much more than placebo up here. And you get insulin release, and you get C-peptide, of course, and insulin secretion rates. But with GIP, nothing really. So all that happened in these co-infusion studies when you did both GIP and GLP-1 was that the inhibition of glucagon secretion that you saw with GLP-1 was abolished by GIP. That is bad. That is not good at all. So this is what happened in these model experiments in people with type 2 diabetes. Now we come to a classical study, concept of GIP. The GIP is in fact an obesity hormone, and that's been good Latin for many, many years, since it was introduced by Vincent Marks back in the 80s. And here's some mice with a knockout of the GIP receptor, and they are resistant to diet-induced obesity. And also, if you knock out the GIP themselves, they're also resistant to obesity, to diet-induced obesity, suggesting that GIP is an obesity hormone, in fact. And we're looking at the adipose tissue. So here we did the same. I mean, I always hated this result here because, as you can see over here, it took 30 weeks before they separated, and that's a long time for a mouse. Now, well, we did it again, and this time it only took just a few weeks of overfeeding before the knockout mice showed a difference from the control mice. So it's real. It's real. We have mutations in people also. And those mutations are associated with low body weight. This is a famous study from Nature Genetics. And in our lab, we have seen, in Meda's lab here, we've seen that those two mutations, they didn't know that, but they don't signal. So this is the signal activity of those receptors, and it's really greatly impaired, as you can see. So no receptor activity, and then you get a leaner body mass. Philip did, with Natasha Bergman, these studies out here to look at the food intake. So again, these are infusions of in obese people of GIP and GLP-1 here to the same kind of solid increases. And again, glucose was clamped here. And the point was to look at food intake, and that's what we have here. So GLP-1 nicely reduced food intake as expected, but adding GIP to this abolished the inhibition by GLP-1, so now we're back to the controls. So certainly not an effect on food intake by GIP. On the contrary, it ruined the good effects of GLP-1. So this was sponsored by Zealand, and they couldn't believe it, so they said, oh, no, we have to have chronic GLP-1 present here. So the same was done again during chronic liraglutide therapy with people in balance in the stable treatment. And so again, GIP was infused here. And here we have the energy intake. And what happened with energy intake in this combination? If anything, there's a rise. There's certainly not an inhibition of food intake with GIP. So what happened when GIP was introduced? Well, what happened was that you had increased triglyceride levels, you had increased glucose levels, and you had increased glucagon levels. So all the bad things. So here is what happened with the GIP antagonist then. And here we're looking at food intake, and in these studies where we're looking at meals and healthy people and the GIP antagonist, nothing happened. So what happened to glucagon secretion in healthy individuals given a meal with the GIP antagonist? Oh, I'm sorry. They had, as you can see here, lower glucagons as opposed to those with Exendin up here, the GLP-1 antagonism. And if we look at adipose tissue blood flow, here is what happens with GIP. You increase the adipose tissue blood flow, and you increase the uptake of triglycerides in the adipose tissue, and you can block that with the antagonist. So we felt that, you know, with here we are looking at triglycerides after a meal with the antagonist, and you can see that you can reduce the triglyceride excursions, and the same is true for chylomicron clearance. So we concluded that GIP promotes obesity and is diabetogenic, in fact, because it enhances intestinal blood flow, it enhances triglyceride absorption, it enhances adipose tissue blood flow, it enhances triglyceride deposition in the tissues, it enhances glucagon secretion, you've seen that. And the antagonist will block all of this. So we think that, on the contrary, this is all the wrong things. Well, there are people with different opinions, and this is the most recent cell metabolism paper about this. This is from a group in Munich, and they think that GIP is very important, and also that it is an appetite inhibiting hormone, and that it has, you know, receptors in the hypothalamus. And here they have created a long-acting GIP that they can inject, and then they can also knock out these neurons very, very elegantly with a technique, so that you no longer have these neurons in the hypothalamus with the GIP receptor. And what they have done then is to look at the effects of this long-acting GIP, and you have it here, and dose response here, and food intake is inhibited. So there are other things. They have also looked at signaling up there. This is C-phos, and here you can see more C-phos here in what is that? That is in the, I think this was in the arcuate nucleus here, and down here you have the ventromedial hypothalamus. These are the nuclei where food intakes are regulated. So all of this ends up with this beautiful slide. On the left, you have a GIP long-acting agonist, GIP agonist developed by Zealand. To the right, you have a GIP antagonist developed by Amgen. And this is what happens with vehicle in these mice. This is what happens with the antagonist, nothing on its own. This is what happens with the agonist, nothing on its own. But then they combine it with liraglutide. Liraglutide causes a body weight drop, as you can see. And then you combine it with the GIP antagonist or the GIP agonist, and then things happen. So isn't that fantastic? You can have exactly opposite, identical curves really, but exactly opposite with the antagonist and the agonist. So nobody can understand that, of course. The possibilities are that the GIP system is prone to desensitization. And that is supported by naturally occurring receptor mutations, if you look at those. And studies with the antagonist show that, this is very remarkable, something happens with the receptor when you block them with an antagonist. So what we're looking at here is the GIP receptor and all its signaling things, but we have to remember that more happens than just cyclic AMP and all that. You also recruit beta-arrestin from these cells. And what the beta-arrestin does is to induce internalization of the receptor. So it's taken in up to the cell, and then it's no longer at the surface, and the cells can't signal. So it's dependent on arrestin, and this is shown here. And it's true for two arrestins, both 1 and 2, and they're both recruited by this. This is all taking place in Rosenkiel's laboratory with the new antagonist. So this new antagonist, what does that do? So first of all, this is where you see the internalization after GIP. And then you give the antagonist, and whoops, it goes down again, and the receptor recycles to the cell surface. So that's what happens. So that's what the antagonist does, and this is something new, and we have to think about this. In fact, here there was a study by this guy here back in 2014, where he looked at, he gave repeated doses of GIP and looked at receptor internalization. So this is with no GIP, there's a receptor out here. This after 15 minutes, there's more inside, and there's more inside. So this is the internalization visualized directly. And then the responsiveness in terms of cyclic AMP, first exposure, large response, second exposure, only half. So there's experimental support for this. And here comes then tirzepatide. So what happens if you do this with tirzepatide? So these are internalization experiments again, and beta-arrestin recruitment experiments. And so this is a study we did together with the people from Eli Lilly, which is, they're the ones with the tirzepatide. And so this is really interesting. And we got these are the results. And we interpret them, completely differently, the group from Lilly and us. But nevertheless, so this is what happened with the GIP receptor exposed to GIP or tirzepatide. Exactly the same thing in terms of internalization, completely identical. Same thing for beta-arrestin recruitment, exactly the same. If you look at the GLP-1 receptor and expose it to GLP-1 or tirzepatide, what then happens? Something dramatically different. The internalization is much, much less with tirzepatide, and the beta-arrestin recruitment is really, really low. So tirzepatide does nothing new, nothing unexpected to the GIP receptor, but the interaction with the GLP-1 receptor is really, really completely different. So that's what we know about it, and you can see this here, because here we have GIP, and these are receptor visualizations in the control after GIP, and you can see there's beautiful internalization of the receptor here, really, really. And tirzepatide, it does exactly the same. Now then look at the GLP-1 here, the GLP-1 receptor. With GLP-1 internalization, it's completely gone from the cell surface. But now with tirzepatide, it's all back to the cell surface. So, all acute GIP infusion studies in humans show unchanged or impaired glucose control in people with type 2 diabetes. No effect on food intake. GIP agonists downregulate and desensitize the GIP receptor in high doses. Does this explain that the agonist and antagonist act the same way? This is what one group proposes. GIP antagonism may impair GIP action on fat uptake deposition and may prevent weight gain. This is what we have shown in others. Both GIP agonism and antagonism enhance GLP-1 action in rodents, and I showed you this beautiful slide with the two set of curves. The GIP actions in tirzepatide are unchanged. Towards the GLP-1 receptor, tirzepatide acts as a biased agonist, that's the term for it, and prevents internalization. And then, of course, there may be differences between mice and humans that we cannot take into account right now. I talked to Dan Drucker yesterday, and he told me that he had exposed his GLP-1 receptor knockout mice to tirzepatide, and in those mice, there was absolutely no effect on body weight. That was all. Thank you.
Thank you so much, Jens, for this fascinating lecture. Are there any questions to Jens from the audience? Mads? I don't know if we can share this.
Yes, thank you, Jens, for this exciting talk. I was at the beginning, I was expecting you to say that we now had a treatment that was even better than GLP-1. I'm not sure I got that impression when you finished. Do you see any future for the combination of this drug?
GIP and GLP-1, no. But tirzepatide is a beautiful drug. I mean, absolutely beautiful. And we still don't know. We don't understand why it affects the GLP-1 receptor the way it does. So something happens intracellular that we simply don't know yet. So if a cell expresses the two receptors at the same time, what happens in that cell when it's activated by a dual agonist? That's the real interesting part here. But both Dan and I agree completely that tirzepatide is, in fact, a GLP-1 super agonist. That's what it is. And that fits with the side effects also.
But Jens, do you think the GIP receptor activating component of tirzepatide is important for the effects of GLP-1 and the internalization?
Yes, somehow I do. I mean, I certainly must take that into account. And, you know, I'm talking to Mette every day about it. And she says, we're working on it.
Because did Dan say anything about a comparison to...
But he's going to give a talk at the ADA here. He will introduce, I think it's a tirzepatide symposium or something like that. And he says that he will come up with some new information. So I don't know.
Because he could compare, you know, a GLP-1 monomolecular GLP-1 receptor agonist.
But you know, it's not every time this happens, because there are 3 other GIP, GLP-1 co-agonists out there, and none of those are interesting at all. Novo did one, was taken off again.
Yeah, I have a question as well to the receptor desensitization. So have anybody compared tirzepatide to liraglutide or semaglutide to look if the desensitization is not the same?
So there are experiments going on trying to compare these things, and some of the results are hidden here, and they're also shown in the articles, and there's no clear conclusion about that so far. Clinically, I'm sure Sten will show this, tirzepatide has been compared to semaglutide and beat the hell out of it, but okay.
But it's because of GLP-1 receptor activity?
Yes.
First of all, I agree that this is a truly fascinating area, this area of physiology. I was wondering about the GIP receptor and the distribution in different tissues, because we talk about, or we have talked about for some years now, the distribution of the GLP-1 receptor in different tissues and whether it's present or not in the kidney and in the brain and in the heart and everything. Yes. What about the GIP receptor?
It's even more confusion. You know, the old studies of the distribution of the GIP also suggest that it's almost everywhere. And in particular, you have it in the adipose tissue, although precisely where it sits and what cells is not completely clear, but it's supposed to be in the adipose tissue. And it's also supposed to be in the brain. I mean, this has been ongoing for a long time. I'm not so sure that there are good human studies about this, but the mouse studies are quite convincing. The question is always, how does it get there? How does it get there? I mean, if you have them in the median eminence, if you have them in the area postrema, then you're safe. I mean, because these peptides, they can get access to those regions. But if you have them sitting in the paraventricular nucleus, you have to consider, how does it get there? Does it get there? I mean, that's the problem.
Any other questions for Jens? Then I would like to ask you a more clinical question, because one of the reasons that the current GLP-1 receptor agonists, they have been so successful, you know, they are overswimming guidelines and all over the place, is because of their cardioprotective effects or the effects of major adverse cardiovascular events. So you showed some results from GIP receptor activation that not really fit very well with a cardioprotective effect. What's your bet on tirzepatide and CVO, cardiovascular outcome trials?
Are you talking about the Leif Grob studies of GIP agonism, where, you know, there's a thickening of the
for instance, yes.
media?
Because, I mean, the only way tirzepatide will survive on the clinical in the clinical field if it reduces major adverse
But
cardiovascular events.
the SURPASS-4, will you be showing SURPASS-4? The cardiovascular outcome trial for tirzepatide. It came out yesterday or something like that. And there is a MACE reduction, a point estimate of 0.81. So it's pretty close to the other. Semaglutide is better, but it's pretty close. It's not significant because it's a pre-registration study. It's different, but it shows the same, you know. So it probably does that, and it doesn't harm. It doesn't seem so.